number 1. The pressure of the vapor phase in equilibrium with an ideal binary solution is P. The liquid phase mole fractions of the two components are x1 and x2, and their respective saturated vapor pressures are P01 and P02. Show that x1 equals P minus P02 divided by P01 minus P02. This is an ideal binary solution where the two liquids are in equilibrium with their respective gaseous species. X1 and X2 are the mole fraction of the two liquids at equilibrium. P is the total vapor pressure at equilibrium. P01 and P02 are the saturated vapor pressures of the respective gaseous components. From the Dalton's law of partial pressures, we can write the total pressure, which is P, equals the partial pressures of the two gaseous components. We can write P1 plus P2. Next, we can substitute values for these two partial pressures using the Raoult's law. According to Raoult's law, partial pressure of gas 1 equals molar fraction in the liquid phase times saturated vapor pressure. Then P2 equals x2 times P02. Now we can substitute these values for the first equation. P equals, instead of P1, we can write x1 P01 plus x2 P02. In this expression, we can see x1 but x2 is not present. Therefore, we need to remove x2 from this expression. x1 plus x2 equals 1. Therefore, x2 equals 1 minus x1. From equation 1, P equals x1 P01 plus x2 is 1 minus x1 times P02. x1 P01 plus P02 minus x1 P02 equals P. P minus P02 equals x1 P01 minus x1 P02. x1 times P01 minus P02. Therefore, x1 equals P minus P02 divided by P01 minus P02. This is the answer for the question number 1. Question number 2. The pressure of the vapor phase in equilibrium with a binary solution containing methanol and ethanol is 4.5 times 10 to the power 4 Pascal at 50 degrees Celsius. At this temperature, the saturated vapor pressures of methanol and ethanol are 5.5 times 10 to the power 4 Pascal and 3 times 10 to the power 4 Pascal respectively. Consider that the solutions behave ideally. This is an ideal binary solution where liquid methanol and liquid ethanol are in equilibrium with gaseous methanol and gaseous ethanol. The saturated vapor pressures of methanol and ethanol as well as the total pressure was given in the question. Question number 2, part 1. Calculate the mole fractions of methanol and ethanol in the liquid phase. We have derived this equation during the question number 1. Here, x1 is the mole fraction in the liquid phase. To calculate this mole fraction, what we need is the total pressure and the two saturated vapor pressures. Therefore, students, we can use the same equation to get the answer for the first part of question number 2. We can write mole fraction of methanol CH3OH in the liquid phase equals, now P is the total pressure, we use PT minus P02, that is saturated vapor pressure of ethanol C2H5OH divided by P01 is the saturated vapor pressure of methanol P0 CH3OH minus saturated vapor pressure of ethanol C2H5OH. Now substitute values for this equation. Total vapor pressure is 4.5 times 10 to the power 4 Pascal minus saturated vapor pressure of ethanol 3 times 10 to the power 4 Pascal divided by saturated vapor pressure of methanol 5.5 times 10 to the power 4 Pascal minus again saturated vapor pressure of ethanol 3 times 10 to the power 4 Pascal. 1.5 times 10 to the power 4 divided by 2.5 times 10 to the power 4. Therefore, mole fraction of methanol in the liquid phase is 0.6. Next, mole fraction of methanol plus mole fraction of ethanol equals 1. Therefore, we can write mole fraction of ethanol C2H5OH in the liquid phase equals 1 minus 0.6. Therefore, the answer is 0.4. Question number 2, part 2. Calculate the mole fractions of methanol and ethanol in the vapor phase. Partial pressures of gaseous methanol and ethanol are required to get this answer, which is the mole fractions of methanol and ethanol in the vapor phase. According to Raoult's law, partial pressure of methanol CH3OH equals mole fraction of methanol in the liquid phase, that is X CH3OH in the liquid phase times saturated vapor pressure of methanol CH3OH. Substitute values for this expression. Mole fraction of methanol in the liquid phase is 0.6 times saturated vapor pressure of methanol 5.5 times 10 to the power 4 Pascal. The answer is 3.3 times 10 to the power 4 Pascal. Next, we can write partial pressure of methanol equals molar fraction of methanol in the gaseous phase CH3OH in the gaseous phase times total pressure. Substitute values. Partial pressure we just calculated 3.3 times 10 to the power 4 Pascal equals molar fraction of methanol in the gaseous phase times the total pressure is 4.5 times 10 to the power 4 Pascal. Molar fraction of methanol in the gaseous phase equals 3.3 divided by 4.5. Because the 10 to the power 4 is cancelled out, the answer is 0.73. Molar fraction of ethanol in the gaseous phase C2H5OH in the gaseous phase is 1 minus 0.73. Therefore, the answer is 0.27. Question number 3. Based on the above calculations and given information, draw the vapor pressure composition diagram of the methanol-ethanol mixture at 50 degrees Celsius. Consider that the solutions behave ideally. First, we have to mark the y-axis as pressure. Next, the x-axis, mole fraction. Compare the saturated vapor pressures of the two gaseous components. Saturated vapor pressure of methanol is greater than that of ethanol. Saturated vapor pressure of methanol is 5.5 times 10 to the power 4 Pascal, whereas saturated vapor pressure of ethanol is 3 times 10 to the power 4 Pascal. Next, we can mark these values on our vapor pressure composition diagram. First, we will mark the saturated vapor pressure of methanol in the vapor pressure composition diagram. Move to the mole fraction, the x-axis. On the left-hand side, mole fraction of methanol is 0. Right-hand side, mole fraction of methanol equals 1. That means here we have pure methanol. Therefore, we can see the saturated vapor pressure of methanol on this y-axis. Now we will mark the value. P0 methanol equals 5.5 times 10 to the power 4 Pascal. Next, we can mark the saturated vapor pressure of ethanol on this vapor pressure composition diagram. Again, move to the x-axis. Here we can see mole fraction of ethanol equals 0 on the right hand side. On the left hand side, mole fraction of ethanol equals 1. That means here we have the pure ethanol sample. Therefore, saturated vapor pressure of ethanol can be marked on this y-axis. Now we can mark the saturated vapor pressure of ethanol and keep this in your mind. This value is less than the saturated vapor pressure of methanol. Now we can complete the vapor pressure composition diagram. This indicates the total pressure, partial pressure of methanol in the given mixtures. This one is the partial pressures of ethanol in the given mixtures. This is the answer for the question number 3.